Okay, in this lecture we're going to cover the section 4.2 material on limits and continuity of functions of several variables. So in our last section we had introduced the idea of a function of several variables, say 2 or more variables. And in the next part of our course we're going to be developing the calculus for these multivariable functions. So we will start by defining the limit of a multivariable function. So let's consider the simplest case where we have a function f of 2 variables. And let's suppose that this function is defined on some disk containing the point AB. So this function is defined on some domain which is containing the point AB. So we would say that the limit of this function, f of xy, as the values of xy approach the specific point AB, is equal to L if the values of the function f of xy can be made arbitrarily close to the number L by taking points xy sufficiently close to the point AB. So just like we would have for the limit of a single variable function, if we can make the value of our function as close as we want to some number L by choosing points sufficiently close to some specific point AB, we say that the limit of that function as xy approaches the point AB is equal to L. And it's denoted in a very similar way to functions, limits of single variable functions. So one important result that we have for functions of 2 or more variables is that each of the limit laws that we've seen from Calculus 1 will also apply to limits of functions for these multiple variables. So that is, the limit of a sum or difference of functions is equal to the sum or difference of the limits. The limit of a product of 2 functions is equal to the product of the limits. The limit of a quotient is equal to the quotient of the limits as long as the limit of the denominator is non-zero. The limit of a constant times a function is equal to the constant times the limit of the function, and so on. So all of the typical limit laws that we've been working with for single variable functions also hold for these multivariable functions. So let's look at some simple examples to start with, and then we'll consider something which is a little bit tricky when we're working with limits of these multivariable functions. So in this first example, we are asked to calculate the given limit, and in part A, we have the limit of some polynomial function of x and y as the point xy is approaching -1, +1. So just as we would for functions of a single variable or polynomial functions of a single variable, well, we know these types of functions are continuous everywhere. So we could evaluate these limits by simply substituting in the given point that xy is approaching. So in this example, we have 2 times x, which is approaching -1, times y, which is approaching 1, plus 3 times x, which was approaching -1, squared. So simplifying, we have -2 plus 3. So we would have a limiting value of 1 here. So just like we would for single variable functions, the first thing that we typically try to evaluate limits of these multivariable functions is to simply plug in the point that we're approaching. Now in part B, we have a limit of a rational function of 2 variables, that is a quotient of 2 polynomials of x and y. So using the limit laws, well, the limit of this quotient should be equal to the quotient of the limits as long as the limit of my denominator is non-zero. So I could take my value that I'm approaching, or the point I'm approaching, 1, 1, and substitute it in for x and y in both the numerator and denominator. And as long as we have a non-zero denominator, or a non-zero limiting value for the denominator, then this limit can be evaluated in that way. So here we were approaching the point 1, 1. So we could try evaluating our function at x and y equals 1. And we have a numerator of 2 and a denominator of 2, so our limiting value is 1. Now in part C, we have a limit, again, of a rational function of two variables, a quotient of two polynomial functions in terms of x and y. And we're taking the limit as xy is approaching the origin, 0, 0. So here we see when we substitute 0 in for x and y, we get a limit of indeterminate form, something of the form 0 over 0. Now, typically, what we're used to doing for these indeterminate forms is applying L'Hopital's rule. However, L'Hopital's rule is a result only for single variable functions. So L'Hopital's rule says we would look at the limit of the quotient of the derivatives of the numerator and denominator. But now that our numerator and denominator are multivariable functions, well, what do we mean by a derivative of a multivariable function? We have not talked about differentiation of these multivariable functions yet. So keep in mind throughout this course that L'Hopital's rule is only a result for functions of a single variable. It does not hold for functions of several variables. So if we can't use L'Hopital's rule, let's think about how else we handled these limits of indeterminate form in Calculus 1. And the first thing that, or the first way that we saw to handle these indeterminate limits was to try factoring our numerator and denominator and see if any terms will cancel. So as we did with our limits in Calculus 1, let's see if we can factor this function. So in the numerator, these first two terms, x squared minus xy, I noticed that I could factor out an x from, and that would leave me with x minus y. And then I'm adding x minus y. So after I factor out x from the first two terms, I've got an x minus y, and then I'm adding this other factor of x minus y, and the entire expression was being divided by x minus y. So if I factor an x minus y from the numerator, I'm left with an x plus 1 all over x minus y. And I can then cancel this factor of x minus y in the numerator and denominator. And I am left with the limit as xy approaches 0, 0 of a polynomial in terms of x plus 1. And now we can evaluate a limit of a polynomial function in terms of x and y by simply evaluating that function at the point that we're approaching, in this case 0, 0. So as x and y approach 0, we're left with 1. So we would have a limiting value of 1 here. Now, the next thing we're going to talk about for these limits of multivariable functions is the case that a limit may not exist as we're approaching a point. And how could we determine that a limit of a function of two variables does not exist? So let us recall a result that we had from Calculus 1. So recall that the limit of a function f of x as x approaches a exists if and only if the left-hand limit and the right-hand limit of that function as x approaches a are the same value. So in order for a two-sided limit to exist, both the left and right-hand limits of the function as we approach some value must be the same. Now, for functions of a single variable, we can only approach a number, say x equals a, from two directions. That is either the left-hand side or the right-hand side. However, for functions of two variables, there are infinitely many ways to approach a point in the plane. So to illustrate that, well, let's say that we're considering the limit of some function of two variables as we approach a point a, b in the xy plane. Well, we can approach from more directions here than simply the left or the right-hand side. So above, when we're talking about functions of a single variable x, well, we only have a single axis for this single variable function. So if we're considering some function, say f of x, we can, or the limit of some function f of x as x approaches a, we can only approach a from the left or the right-hand side. And if we get two different limiting values, as I've shown in my graph here, we would have a limit which does not exist. But for these points in the plane, well, we could approach from the left or the right-hand side. We could approach from above or below. We could approach along these different shaped curves in the xy plane. So in fact, there are infinitely many directions in which we could approach some point. So as we saw from Calculus 1, if the left and right hand limits of a single variable function don't agree at a point, then that limit does not exist. So we have a similar result for functions of several variables. In particular, if the function f of xy approaches a limiting value L1 along some path, let's call it P1, and the values of our function f of xy approach L2 along a path P2 as xy approaches AB, where L1 and L2 are different real numbers, then we would say the limit of this function does not exist. So to illustrate, well, if we're approaching different, if the values of our function are approaching different real numbers as xy approach AB along two different paths in the plane, say P1 and P2, then we would say the limit does not exist. Or equivalently, the only way that a limit exists is if the values of our function approach the same real number regardless of the path that we choose to approach our point AB along. So the next examples that we'll consider will illustrate some functions where a limit may not exist. So in our first example, we're asked to find the limit as xy approaches 0, 0 of the function x squared minus y squared over x squared plus y squared if it exists. Now the first thing that we could do here, of course, is to try to evaluate the function at 0, 0. And we see that we have a limit of indeterminate form, something of the form 0 over 0. And so we could try factoring the numerator and denominator of this function to see if any like terms cancel. But here, if we factor the numerator as x plus y, x minus y, we see that it will not cancel with any factor in the denominator. So this function is already in simplified form. We can't simplify it and then take the limit as we did in our previous example. So instead, let's consider taking the limit of this function along different paths in the xy plane, which would be approaching 0, 0, or which contain the point 0, 0. So typically, the easiest paths that we could consider passing through the origin would be the x or the y axes. So let's consider the limit of this function as xy approaches 0, 0 along the x-axis. Now, the x-axis is the line defined by y equals 0. So if we look at the limit of our function xy approaching 0, 0 of x squared minus y squared over x squared plus y squared, well, if we're considering points on the on the x-axis, that means that our y-coordinate must be 0. So our function reduces to x squared minus 0 squared over x squared plus 0 squared. So we now have a function that depends only on the variable x. So our limit becomes a limit of a single variable function. And as long as x is non-zero, which it isn't, when we're defining a limit, x is only approaching 0, or never equal to 0 for this limit. So if x is non-zero, then I can simplify the factor x squared over x squared, and I'm left with the limiting value of a constant 1 as x approaches 0, and the limit of any constant is just that constant value, in this case 1. Now let's consider what happens with our function if we approach 0, 0 along a different path. So let's consider approaching the origin along the y-axis, which is the line defined by x equals 0. So in this case, we would have the limit of our function as xy approaches 0, 0 would be given by negative y squared over y squared. So if we're working with points on the y-axis, that means that x is 0. So substituting x equals 0 into our function, we're left with negative y squared over y squared. And we're taking the limit now as y approaches 0. We've already set x equal to 0. So as long as y is non-zero, which it's not if we're taking a limit only as we approach 0, then I can factor or simplify the negative y squared over y squared as negative 1. And the limit of this constant value is equal to that constant, negative 1. So we see here that when we approach the origin along the x-axis, we would have a limiting value of 1. However, if we approach the origin along the y-axis, we had a limiting value of negative 1. So since these two values do not agree, that means that the limit does not exist. So a little explanation, I might say, since these limiting values are not equal to one another, the limit does not exist. So this is one way that we can go about showing that a limit of a function of two variables does not exist. Find two different paths along which we get different limiting values. So looking at another one, we're asked to find the limit as xy approaches 0, 0 of 2xy over x squared plus 2y squared if it exists. And again, evaluating this function at 0, 0, we would have a limit of indeterminate form. And we cannot simplify this function any further by factoring and canceling like terms. So we can't evaluate it as we did with our earlier example where we had an indeterminate form. So let's consider the limit of this function as we're approaching 0, 0 along different paths. So as with our last example, let's maybe consider moving along the x-axis, which again is the line y equals 0. So in this case, the limit of our function as xy approaches 0, 0 would be the limit as x approaches 0, since we're setting y equal to 0 for points on the x-axis, and we would have 0 over x squared here. Now, as long as x is not equal to 0, which it is not because we're only taking a limit as x approaches 0, then 0 divided by x squared will always be 0. So I'm left with the limit of a constant value, which is equal to that constant, in this case 0. So let's consider approaching the origin again along the y-axis, which is the line defined by x equals 0. So here, the limit of our function as xy approaches 0, 0 would be equivalent to the limit as y approaches 0, since we're considering, so this reduces to a single variable function since we're considering points only on the y-axis. And setting x equal to 0 in our function, we have 0 over 2y squared. And as long as y is non-zero, which it is not because we're only approaching 0 for this limit, we would have the limit as y approaches 0 of 0. And the limit of a constant value is equal to this constant, in this case 0. So we see that the limit as we approach the origin along the x-axis and the y-axis give the same value of 0. However, that does not mean that the limit is 0. We've only tested two possible paths through the origin. Recall that there are infinitely many ways that we could approach the origin in the xy plane, not just along the x or the y axes. So let's consider another path. Now we could consider approaching the origin along the line where y is equal to x. So along that line, the limit of our function 2xy over x squared plus 2y squared as x approaches 0, 0 will reduce to the limit of a single variable function x, and let's see why. Now if we're working with points on the line y equals x, that means in the definition of my function that y and x are the same. So if I just substitute x in place of y throughout my function, I am left with the function only in terms of x. And if we're approaching the origin, we're going to let x approach 0. So we are left with the limit as x approaches 0 of 2x squared over 3x squared. And since x is non-zero, we can cancel the factor of x squared in the numerator and denominator. And we're left with the limit of the constant value 2/3, which is 2/3. So we can see, of course, here that this limiting value is different from 0, what we found along the paths given by the x or y axes. So we could say here, since 2/3 and 0 are not equivalent, the limit does not exist. All right. So this example illustrating that just because the limiting values of a function agree along two paths, that does not mean that the limit agrees or the limiting value will be the same along every path. So let's consider another example. Here we are asked to find the limit as xy approaches 0, 0 of x squared y over x to the 4th plus y squared if it exists. And again, the first thing that we would try is to substitute 0, 0 in for xy. But again, we see that we would have a limit of indeterminate form, something of the form 0 over 0. So we might try simplifying this function as much as possible by factoring and seeing if like terms cancel. But this function is already in simplified form. It cannot be factored any further. So in this case, let's try considering the limit of this function as xy approaches 0, 0 along different paths. So as we did with our previous examples, let's first consider the limit along the x-axis, which is the line defined by y equals 0. So here, the limit as xy approaches 0, 0 of our function x squared y over x to the 4th plus y squared would reduce to the limit of a single variable function as x approaches 0. So substituting 0 in for y, we would have 0 over x to the 4th, which for every non-zero value of x is 0. So the limit of that constant value gives us 0. Now again, if we were to consider approaching along the y-axis, which is the line defined as x equals 0, the limit of our function as xy approaches 0, 0 will reduce to a limit of a single variable function as y approaches 0, since setting x equals to 0 in our function would leave us with 0 over y squared. Now for every non-zero value of y, 0 over y squared is equal to 0, so we're left with the limit of a constant, which is equal to that constant. So we get the same limiting value along both the x and the y axes. However, as we've seen from the previous example, that does not mean that the limit exists. We have to consider other paths through the origin. So let's think about trying to tackle more than one path at the same time. So to illustrate here, well, in the xy plane, we're taking a limit as we're approaching the origin, 0, 0. And we've already shown that if we approach 0, 0 along the x-axis or along the y-axis, that we will have the same limiting value of 0. Now, in the previous example, we then considered the line y equals x, and we saw that we had a different limiting value. Now let's say that we had the same limit along this path. Well, I would then have to consider maybe a different line passing through the origin. Let's say y equals 2x, or maybe y equals 1/2 x. Or lines with negative slope through the origin, say y equals negative x, and so on. So rather than trying to consider each of these lines as their own special case, let's consider all lines that have this form. So let's say along lines of the form y equals mx. So these would be lines of slope m passing through the origin. So we would have here the limit as xy approaches the origin would be given by the limit of a single variable function, let's say as x approaches 0. Since when I'm considering points on these lines, something of the form y equals mx, if I substitute mx in place of y for my function, I'm left with something only in terms of x. So let's simplify this and see what we have. We would have the limit as x approaches 0 of mx cubed over x to the 4th plus m squared x squared. So if I cancel 2 powers of x from the numerator and denominator, I would be left with mx over x squared plus m squared. So I'm canceling 2 powers of x from both the numerator and denominator. And now, taking the limit as x approaches 0, well, I would have 0 divided by 0 plus m squared, which is 0. So what I find is that the limit along every line through the origin would give me a limiting value of 0. Now, does that mean that the limit is equal to 0? No. Why not? Well, not every path through the origin in the xy plane has to be a line. Remember, as we discussed earlier, we could take different sorts of oddly shaped paths approaching the origin. So if we've shown that we have the same limit along every line through the origin, well, we've not tried every possible path through the origin. So if we've exhausted all of the lines, well, let's try maybe parabolas passing through the origin. Let's say something of the form y equals x squared, the parabola whose vertex is at the origin. So let us consider the limit along the parabola defined by y equals x squared. So if we consider the limit of our function as xy approaches 0, 0, along this parabola, y equals x squared, we can reduce to the limit of a single variable function as x approaches 0. by setting y equal to x squared within our function. So for our numerator, we would have x squared times x squared, or x to the fourth, divided by x to the fourth plus x squared squared would be x to the fourth. So we would have the limit as x approaches 0 of x to the fourth over 2x to the fourth. And since x is only approaching 0, x is not equal to 0, we can cancel this x to the fourth over x to the fourth. And we're left with the limiting value of 1/2, which would be 1/2. And we see here that, of course, this limiting value does not agree with the 0 limiting values that we found along our other paths. So since these two values are not equal, the limit does not exist. So this example illustrating that even if we can show that the limiting value is the same along every line through the origin, if we consider a different path through the origin, we may have a different limiting value, in which case our limit still does not exist. Now, in the last part of this section, we'll talk about the formal definition of continuity for functions of two variables. So let's suppose that we have a function f of xy. We would say that function is continuous at a point a, b, if the limiting value of our function as xy approaches a, b is equal to the value of the function f at a, b. Now, this definition really implies three things, or there's three things that we must check to establish continuity of a function at a point. The first condition is that f of ab must be defined. So the function must be defined at our point ab in order for it to be continuous at that point. The second condition is that the limit of our function has to exist as xy approaches our point of interest ab. Now, if the function is defined at this point and the limit of our function as we approach ab exists, then the last condition for continuity is that that limiting value must be the same as the value of our function at that point. So in our last example, we're asked to show that the function f of xy, which is defined here as a piecewise function, is discontinuous at the origin. So here we have a piecewise defined function of two variables. If xy is equal to 0, 0, then our function is defined as 0. So our function is defined to be 0 at the origin, and for any other point in the xy plane other than 0, 0, our function is defined as 3xy over x squared plus y squared. Now, we claim here that this function is discontinuous at the origin. We're supposed to show why. So let's see which of our three conditions fails. The first condition for continuity is that the function has to be defined at our point of interest, in this case 0, 0. Now, we've already said if xy is equal to 0, 0, then our function is defined as 0. So we see here that the function f of 0, 0 is defined, or the value of our function at 0, 0 is defined. So the first condition holds. The second condition is to show that the limit of our function as xy approaches 0, 0 exists. Now, if we consider the limit as xy approaches 0, 0, we're looking at the limiting value of this function as x and y get closer to 0, 0, and we could see that we would have a limit of indeterminate form, something of the form 0 over 0. And this function cannot, or this function definition cannot be simplified any further. So if we can't simplify, we might try evaluating our limit along different paths. So let us consider the limit along the x-axis, which is the line y equals 0. So if we're taking the limit as xy is approaching 0, 0, but not equal to 0, 0, then we're working with the function definition 3xy over x squared plus y squared. And if we're considering points only on the x-axis, then this would reduce to the limit as x approaches 0 of 0 over x squared, which is simply the limit of a constant 0. So we get a 0 limiting value along the x-axis. Now we can see pretty quickly, if we were to consider approaching about the y-axis, where x is equal to 0, that we would also get a limiting value of 0. So let's try another line. Say along the line y equals x. So here we would have the limit as xy approaches 0, 0 of our function 3xy over x squared plus y squared would be given by the limit of a single variable function as x approaches 0. And here we would have 3x squared over x squared plus x squared, or 2x squared. And as we're approaching 0, we could cancel this factor of x squared over x squared, and we would be left with the limit of a constant 3/2, which would be given by 3/2. So since this limiting value does not agree with the limiting value along the x or the y axes, we could say the limit does not exist. So the second condition for continuity failed. Therefore, our function f is discontinuous at the origin, which is what we wanted to show here. Now in this section, we've been working with the limiting values of functions of two variables. Of course, we could extend these concepts that we're talking about to functions of 3 or more variables in order to define limiting values of functions of 3 or more variables, or to determine when the limit of a function of 3 or more variables does not exist. But in our course, we'll typically focus only on these functions of 2 variables.